My name is Zhao from Southwest General University, China. The title of my presentation today is a study on the coupling of the wheel of the vertical, lateral, and the longitudinal wheel interactions at a high frequency and also the resulting irregular wear. The outlines typical classical 4 parts. First, the background. As it's well known that short-wave irregular wear or irregular plastic deformation is an important issue in the railway. As here I show you the irregular wear problems occurring on the high-speed wheels and rails in China. It's easy to imagine in the presence of these short-wave irregularities, the wheel-rail interaction will be excited at high frequencies. The occurrence, of course, is also related to the high frequencies. And in these cases, the vertical, lateral, and the longitudinal wheel-rail interaction will occur at the same time. In other words, they are coupled from one another. In previous studies, we usually employ steady-state rolling contact theories, such as first theme of Professor Kalliker and Zhang's theory to treat the tangential wheel-rail interaction. And for the normal interaction, we employ the Hertz spring. So from here, we can imagine, we can find the wheel-rail interaction actually was simplified, and the coupling was simplified to a large extent, because the high frequencies is not steady state. It varies with time, but this cannot be considered. So the intention of this work is to better understand this coupling. Yeah, for this purpose, we developed this rolling contact FE model. Maybe somebody follows our work and will know we simulated the transient wheel rolling contact with the finite element. So we use the explicit finite element method. So due to its instability problem, so the very small time steps have to be employed. It's down to -8th power over seconds. So we use these small steps. We can capture the transient effects of the wheel rolling contact in the time domain. The wheels and the rails are meshed with solid elements. So the continuum of vibrations of the wheels and the rails are taken into account together with the structural ones. And finally, we use the wheel surface-to-surface contact to solve the normal and tangential contact problems at the same time. So their coupling was considered inherently. So here's some basic most important parameters. With this model, we can simulate a maximum of 500 kilometers per hour rolling. And rolling sliding is simulated. We apply a drive torque M on the position of where the drive gear is. And so the different traction coefficient can be applied. A free wheel was placed on the track. So all 3 creepage components can be simulated at the same time. And finally, in this work, we mainly we implemented the wear models to further calculate the irregular wear resulting from the high-frequency interactions. 3 models were used, and namely Archard, T-gamma, and Zobris. Yeah, we applied the wear model. Of course, we first to validate it. In the photo, we see the gray box. That's the wear rate we observed from the field. And for this, for the purpose of validation, we simulated a case on the tangent track. And the smooth wheel and the rail is assumed to study the approximately steady-state rolling. A traction coefficient of 0.05 was considered. That's typical. We assume, we think, by some references and literature review, That's the typical, this should be the typical value on the tangent track and shallow curves. Then the simulation speed is 300 kilometers per hour, the typical speed in China, and the friction coefficient 0.3. We carefully modified the friction, the wear coefficient, the K, 3Ks, related to the 3 wear models. And finally, we got the calculated the wear rate. It's indicated by 3 different colors line. And you can see, in this case, we validated the wear model, basically. So with this validated model, we try to understand how the irregular wears come into being from initially nothing, and of course in the presence of vibrations, basically the initiation. For this purpose, we assumed sinusoidal vibrations with a fixed angle, phase angle. 2 frequencies are considered, they corresponding to the 2 corrugation wavelengths that we have found out. 3 different vibrations are considered, the lateral and the vertical with the frequency of 1040 Hertz, and the rotational vibrations with 621. And that's where the red arrows shows where they are applied. I will go further later on. The concrete eigenmodes of these vibrations are not taken into account. We just instead to apply varying forces at the wheel set or the axis to apply study its influence. First, we apply the vertical varying force on the right wheel. That's the calculated irregular wear. The horizontal axis is the longitudinal direction, and the vertical axis is the irregular wear. And the blank line at the bottom is the variation we applied. And the lines of different colors is the irregular wear calculated on the different traction levels. We can see 3 important points here. First, the irregular wear pattern is almost independent of the vibration we applied when free rolling occurs. And for the traction coefficient between 0.02 to about 0.2, their phase are quite stable. And we have, quite stable. And when the full rolling occurs at 0.3 for traction coefficient, there is a significant phase shift. So from here, that's the main thing. That's the wavelength. From the left side, we can see there's no obvious wear pattern was observed from the other side. So this means the vibrations may not can transfer to the other side efficiently. From here, we can try to understand if vertical vibration leads to corrugation necessarily, well, of course, with fixed phase angle. From these results, we say the answer is no. Why? Two points. First, it can only occur on one side. The other point is it can only occur when the traction coefficient is relatively stable. You either for rolling sliding or full sliding. But if you varies between rolling sliding and full sliding, the phase difference will remove the remove the irregular wear probably. So if we see the lateral vibrations, in this case we applied the lateral vibration on the left side, and we see that's the contour of the irregular wear on the left and the right side. You can see, as indicated there, the wavelength on the left side where the force was applied, the wavelength is 40. But on the right side, the wavelength is 80. And the wavelength we applied is 80. So the reason why the 40 wavelength occurs is because on the left side, the lateral force is very large. It varies around 0. So we have both positive and negative peaks. So within one period, 2 wear peaks occurs. That's the right side irregular wear calculated on the different traction coefficients. We can see again the painting of the irregular wear is quite stable below 0.2 traction coefficient. And when we further approach full sliding, there's a significant phase shift. But this phase shift is much slower, much smaller than those of the vertical, in the case of vertical vibrations. So again, we answer the same question. If the lateral vibration with the same phase angle for every passages lead to corrugation necessarily, the answer is probably no either, because again, it's one side, it follows the applied load, but the other side, because positive and negative peaks may be different wavelengths. And the second point is it requires quite stable traction coefficient for the corrugation occurrence. The third, rotational vibrations. For this case, we applied the varying driving torque at the position of the drive gear, and the left side, the right side, and the load applied, the position of the load, and it's closer to the right side. So if you can see here, the irregular wear is larger than the left side, and the right side is larger than the left side. And plus, when the traction coefficient, when the free rolling traction coefficient over 0, you can see also the peaks. There's two wear peaks within one period. It's because of the same region. They varies around 0. But interesting things to say, for the traction variations, there's no phase shift occurs when the traction coefficient increases from rolling sliding to full sliding. So again, a rotational vibration with a fixed phase angle lead to a corrugation? Necessarily, probably yes, because but the wavelength of the corrugation may vary, maybe half of the applied vibration because of both the vertical positive and negative peaks within one period. And the other point is, with the increase of the traction coefficient, its occurrence rate should be faster. And also the rate will be faster on one rear side, where the applied load is close by. So finally, the conclusions. First, we have extended our transient FE rolling current FE model to include wear calculations and validated. Second, for the vertical lateral wheel interactions, we found that they are coupled to a large extent, while the longitudinal one is relatively independent under the rolling sliding conditions, but it becomes dependent on the vertical one when approach full sliding. The third is the magnitude of irregular wear increase monotonically with the traction coefficient. The fourth one, corrugation tends to occur under large and stable traction levels. And probably on one side, it's easier. So finally, this is very close by to my statement. So vibration with a fixed phase angle may not lead to corrugation. That's pretty much my presentation. Thank you for your kind attention.